then it's time for some applications of, well, applications, I suppose. We're going to look at drill string models. It's based on a note by Sigve Hodbra and Espen Ragnes. So drill string. Models. Okay, so how does a drill string look? Usually, it's fastened somewhere, and then you have this pipe going down, different sections perhaps, different radius of it. The thing is, I've never seen a drill pipe in real life, so I hope this is a good representation of it. Okay, so in red here we have the pipes. In blue here, this is the, well, walls. And inside here you will have, let's say in brown, you will have a lot of drill fluid or drill mud going around it. And I suppose also at the end here, you will have a drill bit. Which is what's creating it. Okay, so how would you try to model this? As the big thing in itself, or as a part of many small things? And look at emergent properties. Okay, so if we divide this into blocks of, well, mass and strings between them, but would that represent a drill string? Does that make sense? So if I tell you that my model of a drill string is going to be colors again. It's going to be some kind of string here, spring, then a mass element, new string, two, and then at the end, you have n. That makes sense? So that's going to be our assumption during all of these modelings. So we'll also assume that these are just masses, and they have no height. They will only have a width. That is kind of in physical. But if we have more than enough of them, let's say n of them, they should represent the drill string fairly okay. No? And then each of these strings, strings, they obey Hooke's law. Obey. That is to say, the force on them equals some kind of spring constant times mass. No, let's see. No. Of course, not m, something else. Okay, and then we'll also say that they have zero length. So it's actually more like block. Well, let's see. String, block, string, block string, and then the last block down here. That's more like our model. But we're just gonna assume them like this. And then the length between each of them is going to be h. So between two is h, or the length between them. We're also going to say that the total length of the drill string is L. Going to be a lot of variables today, so please bear with me. And then each of the different blocks can have different cross sections. That represents the variable sizes in the drill string. I assume it's not as protruding as this, but something like this. And also say that there's no angular momentum. So the blocks themselves, they're free to spin like this without storing angular momentum. You know that you can just spin the, call them disks, many times as you want, and you don't store up any energy. It makes it a lot easier for most of them. And then we will say that the first block position, or the origo, this. So this P, that's the coordinate for each of the blocks. Take I. Call this block with 1 already. Okay, so call it 1. For the first block, we have such that time 0, the 1 starts 0. So that's just the origin. We just have to define something. Okay. And then we say that, no, let's say, we start at 0 instead. Makes the math easier later. So 0, 1. Okay, so we're going to say that the block at an I of time t, when it's in equilibrium, it's at position IH. That's when it's in equilibrium. And this is a kind of unrealistic assumption. Thus, there will always be some kind of tension or something along the drill string, or you'll apply some kind of force of it. It would always be not in equilibrium. So we'll say that it's displaced by small qi time, where this qi t, we can call it relative displacement. Equilibrium, that's with 1L, no? Turning it all off, but that's fine. Okay, so the physical state of each element here is defined by, well, qi and its starting position. Lowercase q and its starting position. Okay, so to begin with, we have to see the forces acting on each block. And there are two kind of special blocks in this system. So what are two special blocks in this system? Well, the first one, that's only connected to the top. It's also where we have the driving force. And the last one, there's nothing below it. So those two are special cases. Starting from the top one, look at the forces on the first block. We're going to draw it as a block again, even though it has, well, height 0. Have this with the colors. And M1 down here as well. Okay, so we have some kind of force from this spring going in this direction. Maybe I can colors for this. Call this force F1. It's pointing upwards again. Zero and 0, and then we have 1 here. And then we have a force from the spring as well, going downwards. F2, and it has a mass. So gravity will pull it downwards. A force there, pull 3 or G if you want, and also a kind of buoyancy force or functional. Well, no. No. It's a functional force. So a functional force, that is when you're pressing it down. We're actually drilling it down. That's also going to be on the whole thing. List them. F1, well, what's this going to be? Well, they obey Hooke's law. The first one is minus K1, then delta Z. I forgot to actually say the dimensions here. We'll say that Z goes downwards. F2 is acting in the opposite direction. 1 delta Z is 3. Here we have kind of buoyancy also. mg times the buoyancy factor. Just call it B0. Because you will also have, the mass is pressing it down, but the buoyant forces will try to lift it. Kind of like when you float a rubber ducky on top of water. This will often be equal to 1, except when the pipe diameter is changing, and this sometimes changes also. Okay, so we have all the forces, then we have to look at the sum of all forces. Oh, sorry, yes, I forgot F4. We're just going to call it R1, which is frictional forces. So we'll come back to R1. This is just a placeholder. We'll come back to it. It's going to be frictional forces. So we can use Newton's second law. basically says sum of all forces equals mass acceleration. Or in our case, also m times u equals 0, so it's the first, 2 times differentiated. Okay, what do we get here? Well, first one, we got m0 it's equals minus 1. First one, k0 delta z. Well, that's how far away it is from equilibrium. Again. Excuse me. Oh, we can do this first. Plus k1. Also needs. Okay, so this is delta z. That's relative displacement up here and down there. But we'll just mark them as 0 and then onwards. K1 delta z 0 and 1. Then we have gravity with the buoyancy 0 times g times this buoyancy factor. And the last one is R1. This are called frictional forces. Okay, so this one is going to be equal to 0 minus Q. No, let's see. Oh, no, Q. Just Q. That's the starting point here. Next one is going to be the difference in this one and the next one. Placement. Q0 minus Q1 minus Q0. So, and we can solve this setting it equal to 0, and in total we'll get 0, Q0, of course, plus M0, P0 minus Q0, just Q0 minus. Now we start, then 1, Q1 minus Q0. By doing something with never mind. Plus yeah, just plus R1. I think that should be the same as in my notes. Yep, equals 0. That's for the first block. Okay, and then block number I, where I is, well, the next one and the next, except the last one, is going to be fairly similar. I'll skip some of the forces. Or not skip them, but derivation of them. Or block I, say I is less than 0 and I is less than, no more than 0, so not the first one, it's not the last one. I Again, we'll have there and a straight there. We will have, well, point F1 going upwards. So I know I use the same numbers for these blocks, but it's not the same process over there. It's just contained in itself. F2, and then we have gravity, buoyancy, 3, and the so-called, should I call it again? Frictional forces. F4 equals RI. Like this. Okay? Doing Newton's second law on this. Get that I placement 2 times differentiated of this ith block plus the buoyancy with gravity mi yes minus ai qi minus qi 1. You see what this is? This is kind of how much the spring is stretched. These q's. Then 2 more. Plus ai plus 1 qi plus 1 minus I plus Ri equals 0. Okay. And then we only need one more. And that's the last block. And what's missing in the last block? Well, of course, down here. Suppose we should do it properly. So, last block. Okay, gonna be this. And again, a blue spring. So we'll have force going up here. 1, gravity and buoyancy forces. 2, and this frictional force going down here. F. They want to call it F4, so skipping. No, skipping F2. Don't have that one. Okay, doing the whole thing similar to first and the, well, second to last one. We end up with M, N, Q, and 2 again, so Newton's second law, plus M, N, G, buoyancy force of N, K, N, Q, N minus 1, plus N, 0. Then we have all of our equations. So do you want me to sum all of them up? Yes, I should. We can compare them. So the first one, we will have 0 plus M0 0 K0 0 big Q starting position K1 Q1 0 plus 1. First, and we have block A. 1 1 2 I M I G I K I U I. So the only difference is this first term. This is where it starts. Like this is where this capital Q, that's where the string starts. If you change it in time also. Okay. 1 Qi plus minus I plus Ri. And the last one, basically what's over there, so minus M and Q and M G N minus N Q 1 plus there, all of them. Okay, so what we don't really know here is these viscous forces, Rn. We'll try to figure out what they are, as we can't really solve anything here. Suppose this is okay to take away. Those are viscous friction force. When we try to push on something, it pushes back. We have kind of friction right here. Our eyes. So what can we assume? We'll assume that the drill mud around the drill string is Newtonian. So what's a non-Newtonian fluid? Have you ever played with cornstarch? and water. If you hit it really hard, it's hard, and if you poke it slowly, it kind of separates. So that means you have to pay attention to the the derivative of your force with respect to time. So we just said it is a Newtonian fluid. For instance, honey is a very viscous fluid, but as far as I know, it's Newtonian. So, or just oil, very thick oil is viscous, but it's Newtonian. We also say that this implies that the flow is laminar. So not a lot of turbulence going on. Laminar flow, so it's also steady and axially symmetric. Oh, symmetric. So what I mean with axially symmetric flow? Well, if you have your drill string going down here, you will have equal amount of flow around all of it. Not a good. But the flow will flow equal around it. So it won't have like one side of the drill string where there's more flow than the other one. It's basically just a steady stream of fluid. Meaning that all radial components are 0. Basically a very easy flow. Okay, so assuming this, we can use Navier-Stokes. Says that the pressure inside the cell Pi is only a function of the axial coordinate r. In the well, it's only a function of the axial coordinate r. Okay, then we can actually apply Navier-Stokes. We should get R, the R, and I'll explain all the terms after I've written them. U, I, R, over mu, the I, Z minus rho, the density of the mud, G. R, let me just make a list. R, this is the distance from the center of the hole. Hole. Next, we will have small ui, which we call the axial velocity component. ratio the component of a fluid particle. Oop. What do I mean with this? Basically, how quick the fluid is flowing through somewhere. Next is mu, viscosity. Viscosity, and this rho m density. So this I means that it's related to which block we are at. And then it's also a function of r. It's a function of how far away we are. Okay, so we can do something with this. We can actually solve it, or we can try to integrate it twice. Then we will get a expression for, and well, we will integrate it twice and get an expression for this axial velocity component of the fluid particle. Twice. And also, if this seems mysterious to you, it's Navier-Stokes. So it's just looked up. We get that ui, function of r, or that is a actual velocity component of a fluid particle, it's a function of r, equals this I z. So that's how the pressure is changing as a function of depth, rho m g, for u r squared plus some kind of constant, 1 ln of r. Okay, and then we will take the calling this thing big U y. No, not including the r squared. It's only this bit. Only this bit. So we write it U r big U I r squared E1 ln r plus E2. That's looks a bit more, well, it is simpler than this. Only thing we have to actually calculate is I as well. So yes, there's going to be a lot of different variables here, but I will try to make it easier and easier to boil something down. So, yep, I can do this before the break. What we can imagine is this annulus. Imagine that's a circle. So here is your, this is solid rock. So this is your wall around here. This is your drill string inside here. And radius all the way. We're going to call R. And then we have drawing. And then we have this, which starts from the outside of it. We'll call this alpha I R. That's what's outside. So we have that. We will assume a no-slip condition. So it's a no-slip condition. That means that this Ui of big R equals 0. It basically means that the flow here, so this is looking from the top, drill string, and drill mud inside here, and then you have flow going into the plane. So saying that Ui of big R equals 0, that's a no-slip condition. So right by the edge here, there's no flow. A common assumption. Then we'll say that I R. Oh, no, never mind. This is wrong. My drawing is wrong, so inside here, I R. A lot more sense. This is basically the movement of the drill string at position. Yeah, this should be inside, not outside. Basically says that, well, again, no slip. The fluid is stuck to the edges of my drill string. Again, this alpha then is between 0 and 1. Basically, how big of a proportion the drill string takes in the hole. Guess you could actually start at 0 if you want. Saying that you don't have any string at all. Okay, questions before break? No?